right, in our last chapter we talked a lot about electronic configuration, but what I want to do today is do a little bit of review. So let's do a little bit of practice, and we'll go over some information we covered in the last chapter, just really quick because it does apply to this chapter. So let's do the electronic configuration for sodium. And sodium's elemental symbol is just Na in this case. And if we think about the periodic table, we can go ahead and do this pretty quickly. So I'm just going to paste this periodic table in here so that we get a little bit of review. And if you remember, we've got sodium down here on the periodic table, atomic number 11. So what I like to do is just label each of these. And we said 1s is here, 2s is right there, and 3s, excuse me, is right here. So this is our S block. All right, and over here we've got our P block. And this P block, like we said, starts at 2P, and then we go to 3P. And then over here, helium is kind of the outlier of our 1s block. Okay, so to get to sodium, we're going to pass through this 1s block. So we know immediately that this is going to be 1s2 because we've gone 2 boxes over, we got 2 electrons. Then we'll continue going over through the 2s block. So we'll say, all right, the 2s block also has 2 electrons. And then we go over to the 2p block and pass all the way through it. So we can say, all right, the 2p has 6 electrons, meaning we've passed 6 spaces over. And then we get all the way to sodium, which is in the 3s position, and we only have 1 electron. All right, so this works pretty well, but as I mentioned in the previous video, a simpler thing you can do is to find the noble gas preceding your element. And what I mean by that is work your way backwards from sodium until you find a noble gas. So in this case, we've got sodium, that's atomic number 11, so let's work backwards. So in this case, you can see that neon is the closest noble gas. And in fact, the electronic configuration for neon is really what I have shown in purple here. So this section right here is going to be neon. So another way of writing this is to just say, all right, this is the same as neon that I've got highlighted in yellow. So I'm just going to abbreviate it as Ne. Okay, and then the leftover orbitals would be 3s with 1 electron. So this is called the abbreviated electronic configuration. And it's a lot easier to write it out this way. Like I said, just work your way backwards till you find the nearest noble gas, and then add on your remaining orbitals from there. It's a lot easier to do this. All right, so that's one thing I wanted to review. Another thing that I wanted to review too, before we get too much further in this chapter, is that valence electrons are going to be your highest energy electrons. So valence shell electrons are electrons in the outermost shell. Another way of thinking about this is that they have the highest N value. And if you remember, the shell number we said is the number that goes in front of the orbital. So for example, up here, we have 3. That's the shell value for this one, right? So if we look at it, 3 is going to be the highest shell in this electronic configuration. So in this case, let's even write it down. We said that in this case, neon was our noble gas configuration, and then we had 3s1. That this 3 is the highest N value, meaning that these are the outermost electrons. These are the electrons that do reactions. They're the most interesting electrons within a given element. All right, and so these are the electrons we're really going to be looking at throughout this chapter, are these outermost highest energy electrons. And what I want to start with is by going over a new system called Lewis structure. And this is named after a chemist named Gilbert Lewis, who started studying how these different elements actually bond to one another. And there's two different types of bonding, or I should say two main types of bonding, and we'll talk more about those within this chapter. But the idea with a Lewis structure is that you have a representation of an atom or ion using elemental symbols and dots representing valence electrons. So some of you, if you've taken chemistry in high school, you may have actually seen this. So let's take a look at an example here. So the example we'll use is just that same sodium example. So we said that sodium is represented by the electronic configuration, or abbreviated electronic configuration, that looks like this, right? So in this case, we have one valence electron. Okay, so what we need to do is we need to turn this into a Lewis dot structure. So the Lewis structure is pretty easy to draw. In order to draw this, you would just use the symbol for sodium, which is Na. Make sure you don't do neon. I see this mixed up a lot where students will put the noble gas. Instead, we want to use the elemental symbol for sodium itself down here, right? So sodium is Na, and then we have one valence electron. So to represent that one valence electron, we just draw a dot like this. So this would be the Lewis structure for sodium. The one dot means one electron. If you had two valence electrons, we'd do two dots. If we had three, we'd do three, and then so on. So not too bad. All right, so I'll show you an easy trick. So easy trick for finding the number of valence electrons without going through all this hassle. Number of valence electrons. All right, and this one requires a periodic table, so I'm just going to go ahead and paste my periodic table in here. And I've got my periodic table, but it's really easy. What it says is the Roman numerals and the Roman numerals are used for groups, right? So the vertical columns preceding the letter A are the same as the number of valence electrons. Okay, so let's take a look at what I mean by this, and I'm just going to scoot this down more and blow it up a bit. All right, so if we look at this group 1, right, so that's 1A. This indicates that everything in this column, meaning everything underneath hydrogen, each has one valence electron. Then over here we got 2A. So again, there's an A in it. So I would go ahead and I would say this column, all of these elements have two valence electrons. Meaning if we were to do the Lewis dot structure, we'd do two dots rather than one. All of these down here we don't do because these have B's, so we're going to ignore those. These are the transition elements. We'll just ignore these for valence. And then we'll hop over here to 3A, and as you can imagine, this has 3 valence electrons, and then over here this would be 4, this would be 5, this would be 6, this would be 7, and this would be 8. So if you have a periodic table, you can quickly just look at it and determine the number of valence electrons. So let's just pick one. So for example, selenium. If I look at that, I'd say, well, that's in group 6A, so it must have 6 valence electrons. When I do my Lewis structure, I'd have the element symbol Se with 6 dots around it. So let's try that. Okay, so I'd say Se, and the rules for this are pretty straightforward. You want to do 1 dot on each side first. So I go 1, 2, 3, 4. So there's 4 sides to the element, but we need 2 more electrons. Then we start pairing. So I go 1, 2 extra, and now we're at 6 total dots around selenium. All right, so hopefully that makes sense. I find this a lot easier than going through the electronic configuration, but I thought it wouldn't hurt to review some of these. All right, let's do a little bit of practice. All right, let's do carbon first, and let's just go and look at the periodic table. So if we look for carbon on the periodic table, it's right here. So it should have 4 electrons. So let's go ahead and take the elemental symbol for C and put 4 electrons around it. Like I said, do 1 dot on each side until all sides are occupied. In this case, we only have 4 valence electrons, so we just cover all 4 corners. All right, let's do aluminum. All right, let's go back to our periodic table and look at aluminum. Up here, aluminum is right here, so we must have 3 valence electrons for aluminum. And the elemental symbol for aluminum is just Al. So not too bad, we'll just do Al. And we'll do 1 dot on each side, but we only have 3 electrons, so that would be my Lewis structure for aluminum. All right, let's do another one. Let's do chlorine. All right, chlorine over here is elemental symbol Cl. So this must have 7 valence electrons. So let's go ahead and put this in. So it must be elemental symbol Cl, 7 valence electrons. We go 1, 2, 3, 4, 5. So now we're starting to pair. 6, we're pairing that one. And then 7, we're pairing this one. So this would be the Lewis structure for chlorine. I tend to overemphasize my dots, but you're welcome to just do smaller dots if you'd like. All right, I hope that makes sense, but let me know if you have any questions.